Alrighty. Let's do this. Another day, another month, another problem. Okay. Predict the winner. Medium. You're given an integer array nums. Two players are playing a game. Player one, player two. Player one takes turn. They take turn. Player one starts. Both players start the score with zero. Start the game with zero score. Each turn, the player takes one of the numbers from either end of the array. Nums at 0 or nums at length minus 1, which reduces the size of the array by 1. The player adds the chosen number to their score. The game ends when there's no elements in the array. Return true if the player 1 can win. If the scores of both players are equal, then player 1 is still the winner. You may assume that both players are playing optimally. So return true if player 1 can win the game. So player 1 obviously hasn't. Obviously, I would assume that they have the advantage because they have the first term and the length of the array could be 1 at the very least. And if the array is 2, then they should at most tie or at least tie. So here, okay, this is a case where player 1 cannot win because whatever they do will allow the player 2 to get the 5. Yeah. This one, player 1 doesn't want to do the 7 because then player 2 does 233. So player 1 does the 1, and then player 2 gets stuck with either 5 or 7, then player 1 gets 233. Okay. All right. Pretty straightforward. Length is only 20. Okay. It sounds like I was gonna say this is gonna be something that is not backtracking, but backtracking generally does apply to things that are length small like this. So this might be backtracking. This might be backtracking. All right, let's try to do this quickly. Whoops, forgot to set it up. Uh, um, so you do one or the other. You code the front or the back. Each time it's one or the other option. There's like maybe 2 to the 20th, maybe 2 to the 20th options. Backtracking is generally even shorter than 20, maybe. I actually don't have that great a feel as to what the time complexity of backtracking algorithms are. Okay, in any case, so choose one or the other. How to model this of an array? I almost feel like you should use convert the array into double-ended queue, so then you can quickly access either the front or back and pop them off. Pop it off the queue. Front end, back end. So first, you have two options, 0 and n minus 1. And then if let's say you take the 0, then you have two options, 1 and n minus 1. Huh. This seems so simple. So very simple. Like the recursion would obviously stop if the indices are the same, so therefore you can only take one item. At that point you should be able to evaluate. You should be able to recurse back, or you should be able to pop that stack off of the recursion. And then from there, you evaluate both sides of it. But 2 to the 20th is just too big. I think, oh wait, 2 to the 20th is just 1,000 times 1,000, right? Because 2 to the 10th is 1,000. 1,000 times 1,000 is a million. The 2 to 20th path should be fine. Okay, that's not too bad. The backtracking algorithm, okay. I guess I was that's what I'm saying when I say that I don't have that great a feel at times. Like if it was 3 to the 20th, then I think that might be too big. 3 to the 10th is, or let's see, 3 to the what's a good branching point between 3 to a power and 2 to a power? 27, 81, 273. 273 is kind of close to 256, right? It's not off by that much. So 3 to the 5th is 273. Is that right? No, no, it's 243. What am I doing? 243 is 3 to the 5th, and 256 is 2 to the 8th. Whatever. Backtrack. I think I need to have indices. Okay, yeah, actually now that I think about it, I think I just need to have indices of the start and end. I don't want to pop it off. I actually want to keep it on the stack or keep it on the array and just model the or mimic the available choices based on the start and indices. So let's say front index and back index. I do need to have as parameters the scores. So that's what, say, P1 score and P2 score. And this is going to return true or false for whether or not the player one wins. Okay, so returns. This is going to take options for indices to be played, the front and back, and then and current score, P1 and P2, returns true if player one wins. Okay, and then I always do recursion. I generally do recursion by base case. So this is the no recurse return. So this evaluates if only one option left. If only one option left, then that means that the player takes that option and then the scores can be evaluated, right? So if the front index is equal to the back index, then I guess I need to say whose turn this is. Maybe I can do a Boolean for whose turn this is. I can also do an evaluation as to, based on the size of the array and the remaining elements. I guess I should just pass a Boolean here. So I'll just do, let's say, um, turn is bool and actually let's say current and P1's turn. So if it's true, then it's P1's turn. If front equals back, then ooh, I actually want to. Okay, this is this is gonna be a little hacky, but this is how I like to approach things. A little hacky. I'm going to do P1's turn is P1's turn bool is actually equal to 1. No, equal to 0. So if the turn is 0, then then it's P1's turn. The turn is 1, then it's and I'm actually going to make the scores is going to be an array so that I can index into the array. Scores array. This is going to be P1, P2 values. Actually, if that's an array, then I wonder if I don't need to actually pass it each time. That's because then I have to copy it. Because this is going to be like def first search. This is going to be def first search, so I don't need to actually, I can actually, okay. Now I'm getting into the weeds. Um, yeah, Okay. Yeah, okay. I'm gonna try to do this without the actual thing, without the scores array, because the scores array could be just a memory location that I can access. That is that's carried through globally, but the indices definitely cannot be carried through. Okay. Okay, so backtrack. So here's how this is going to work. If the front equals the back, then scores at the turn index, which is either 0, 1, 0 for player 1's turn, 1 for player 2 turn, is going to increment by the nums at this index, which is the same as front or back. It's going to be the same. And then I evaluate. Um, P1 win is true if scores at 0 is greater than scores at 1. And a tie means that P1 doesn't win, right? So P1 when scores at 0 is greater than scores at 1. And then I'm going to actually I'm going to take back this incrementing of the values because when it backtracks, it needs to return it into a prior state for the scores. And then this is now going to just return P11. And then this is the recursive case where it's not, there's still moves to be remaining. So let's just, well, there's really only two options. Either they take from the front or they take from the back, right? So let's say option 1, take from front. And scores of this player increments by the nums at the front. And now backtrack, take from front, recurse, basically. And then say P1 win. In this case, P1 win option 1 is going to be based on backtracking to front +1 as the index, back the same index. Turn is going to be 1 minus turn. So if it's 0, then it becomes 1. If it's 1, it becomes 0. And then now again, it removes this option, or removes this play from consideration. And now this is option 2. Take from the back, curse, check to see who wins. Actually, no. I don't need to do this like this. Because if the player I think I need to check both options. Let me think. I don't think I need to check the later option if player 1, no, I think I need to check both options, right? Get the feeling maybe there's a slight optimization here that I can not check the second option if one player wins, then it matches themselves, maybe? No, I think it has to be the other option. I need to check both options because it needs to take the worst outcome, almost. It needs to take the outcome that is best for it. Yeah. Well, if it takes the option that's best for it. So if player 2 takes option 1 and finds that player 1 doesn't win in that option, then player 2 would always just take option 1. Like, why would they ever check for option 2? Similarly, if player 1 takes option 1 and finds that they win, then player 1 would never check the second option. They'd only check the second option if they didn't win on the first one, right? So if I'm in that case, okay. If P1 win and the turn equals 0, or there has to be some sort of better way of doing this, or not P1 win and turn equals 1. Okay, there has to be some simplification to this logic. So P1, if it's true, so 1 P1 win is true. P1 win is true. I almost wanted to return a value that is 0 if 0 wins and 1 if 1 wins. Because then I can compare that to 0 and 0 and 1 to 1 here. Yeah, maybe to return 0 if P1 wins. 1 if P2 wins. Because then I can do P1 win is scores grid. So return 0 if P1 win, else 1. That's fine. Oh, this is not the right syntax. Whoops, what am I doing? Okay, and then I can just say here if it matches, right? If the turn matches the player that wins. If turn equals the, I guess I can call this the winning player. What was that logic before? Yeah, yeah. If turn matches the winning player. So this is the win player. Then just return this winning player, right? And then here scores at the back end increments by, oh, sorry, what am I doing? Scores of the player whose turn it is increments by nums at the back end. And then the winning player is equal to backtrack. Front plus one, or no, front, back minus one. And no, what am I doing? Back is like 10 to 9, back minus one. And then one minus turn to alternate the player. Scores at this turn, decrements from this thing. I wonder, yeah, I think that's right. That's right. And then just return whoever wins here. Because if it didn't, if this didn't hit here, then it has to be taken this one here. Either this current player or the other player. Yeah, you shortcut based on if you find you can already win based on your first move. Okay. And then now to just call the backtrack. I guess this is return if the backtracking algorithm from starting index is, oh, whoops, I need to actually set the array. Scores is equal to 0, 0. The backtrack from 0, length of the array, minus 1 as the ending index, and then as the back index, and turn is 0. And if this returns 0, then that means that player 1 wins. I think this works. Mistype scores, excellent. Mistype nums, excellent. Okay. Interesting. 0. How does player 1 win in that case? What? Isn't the score 0, 0? Both players start with score 0. At each turn, the player takes one of the numbers from either end of the array, reduces size array by 1. The player adds the chosen number to their score. The game ends when there are no more elements in the array. Player who wins? If the score is ties goes to player 1. Whoops, I totally watched that. Um, so P1 when if scores is 0 is greater than or equal to. Okay. Okay, yeah. My bad. What? What now? Mother. Guess there were some really bad solutions or, that made the graph look like this, even though there's like a lot of distribution right here. Huh. Okay, so earliest solution looks like 18 milliseconds. That does seem like it would be, that does seem pretty fast. I'm not sure how you'd ever do backtracking that fast. I mean, I think you could do something where it's stack recursion rather than function recursion, or like you use a stack to mimic the recursion. But even then, I feel like this is 20 on the stack, 20 on the stack. I wonder if there's just a mathematical way to do this to mimic the simu. Mathematical way to just look at the array and maybe solve it. But if that was the case, then it'd be much faster than 18 milliseconds, right? It's 20 size array. If you could just process it like linearly by just looking at the array one pass or whatever, or even 20 passes, I guess, that would still be much faster than 18 milliseconds, especially with this small of a sample size or small of a test cases. There's only what um, do they tell you how many test cases? 62 test cases. So yeah, I feel like it has to be kind of exponential almost, in order for it to take 50 milliseconds. I mean, I feel like wonder if I can get rid of this if statement, right? Maybe. P1 scores. I feel like I kind of tamped down on the number of if statements too. Like there's not even an if statement here. It's all indexing. There is an if statement here, but I think that's quite useful. No if statements here. There is an if statement here, and there is recursion. But ends quickly. Ends quickly enough. You don't always want to take the biggest thing. You obviously don't want to take the biggest thing each time, because that could access a even bigger thing for your opponent. So it's definitely not a greedy approach. So if I think about this as some sort of chain, 2 branches, or a tree, 2 branches on the first choice, 2 branches on the second choice for each of those first choices. 2 branches, 2 branches, 2 branches, 2 branches. You dive depth first, see if it's a win. Alternate. P1 wins equals scores at 0 greater than scores at 1 greater than or equal to. I wonder. I wonder if you can just return P1 win. No. Do you want to convert that into? I see how I could maybe make that slightly. No. Okay, I think I want to just for Python, do bools convert or do bools do true Boolean convert to be 1? I guess I kind of want this. Okay. So I think I could do not this. Or I can do just P2 win as scores at 0 less than or equal to scores at 1. Yeah, maybe that's better. Okay, I mean, I got rid of an if statement. Oh, whoops, this should be just scores at 0 less than scores at 1 because ties goes to P1. Do 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 do. All right, 1 millisecond worse. Excellent. Excellent. Front, back, front, back, front, back. Turn alternates. 1 0 0 1 1 0 0 1. All right, I am done. I am done, 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 done. All right, summary. This is going to be. I'll start with saying not sure how to make this faster. I'm pretty sure this should be some backtracking kind of recursion deal. Maybe using a stack instead of recursion. A stack, kind of a state stack, where the state of the indices that are being used are like tuples on the stack. Might be better since there might be some overhead. Then there might be some overhead and function calls that are slower than stack manipulation. Anyways, used use scores, use an array to track the scores. When passing info into the function, the backtracking function. included which indices are available to be front and back, and whose turn it is. Technically, um, technically, turn can be deduced from like the length of the array and the front and back indices because then you can see how many turns are left and how many turns were there originally, and then like do some sort of calculation there. So technically turn is not necessary as a parameter, but it's just convenient. In any case, so for recursion, for the backtrack function, base case is when front equals back, so only one option. Can evaluate and return. Here, the return is actually the number of the player who wins, 0 for player 1, 1 for player 2, or basically 1 if P2 wins, or like basically a boolean for when that P2 wins. So that's this base case, and then the recursive case breaks down into two things. Recursive case has two options. One for taking from the front, and other for taking from the back. Make sure to remove the score increments when changing options, or yeah. So you always want to leave the score values back into their pristine state before you kind of evaluate a different option or different branch in the choice tree. Complexity is going to be O of 2 to the power of n, since we're basically checking every possible choice path in a depth first search fashion. So like in theory, it could be like you're checking player 1 chooses the front, player 2 chooses the front, player 3 chooses front, player 4 chooses front, all the way into the end. There is this earlier check to see if the player whose turn it is can win with their current play, so then they wouldn't check the second play. But that's just an optimization. That it could be that they can't figure that out until the very end. Space complexity can be O of 1, since I'll say this is O of n, since even though scores is too long array, two integers, the stack size, the recursion will be n depth, and that'll take memory. All right.